So this is the general version of the reaction. Just I would put H minus in brackets for reduction, because it's a reduction, right? We talked last week about the real quick sort of just rule of thumb that you can use in organic chemistry to decide was a reaction a reduction or not. Or last week it was an oxidation. This week we're looking at the reduction. So we said the reverse of our test last week for oxidation reactions is to look at a particular carbon that might have gotten reduced on the molecule and say, did it get less bonds to oxygen? Then it's a reduction reaction. Or did it get more bonds to hydrogen? Then it's you only need one of those two things to be true for it to be a reduction reaction, right? Is that the case here? Yeah, they're both the case, right? Actually, we got less bonds to oxygen, and we have a new bond to hydrogen right there. So it passes both of the tests, even though it only needs to pass one. All right. And in the second, I'll show you. So we're doing kind of a fancy reduction of ethyl acetoacetate. In a second, I'll show you just sort of the more run-of-the-mill type of reduction that we would do. If we would do the easiest way to do it is actually just plain old sodium borohydride and no tartaric acid. Okay, so I'll talk to you a little bit about that, because that's more the kinds of ones that you're going to be learning in the lecture course. Okay, and then we'll talk about the fancy one that we did today. But before I do that, I wanted to ask you, is the product chiral? Is that a chiral molecule? Got one vote for no. I got a lot of abstains. Anybody else? Is it chiral? I think in this class I talked about this. It's the worst memory ever. In first semester I talked about this, so some of you that weren't in here with me. So there's a bunch of there's 3 different tests for is a molecule chiral. Okay? One, you can draw a mirror plane, draw the mirror image, and then if you can't superimpose them, if you can't morph them together, it's chiral molecule. Okay? And that actually would fail in this situation. Okay? So that's not the best test. The second test is probably the test that like I myself use the most often, but it also fails 5% of the time. So I double check it with test 3. Okay? Test 2, which is the one I use the most personally and stuff, is does the product have a chiral center? Okay, I have 1 yes, 7 abstains. Come on, take a stand. No Switzerland's in here. Okay, I have 2 yeses. All you need, don't overthink it, all you need for a chiral center is a carbon that has 4 different things attached to it. And yeah, that carbon right there, it's got a CH3, it's got all that junk, it's got an oxygen, and then it's got an H that I didn't draw in, but it's still a 4th thing. That's a chiral center. 97.354, I made that up. Percent of the time, if a molecule has a chiral center, the molecule itself is a chiral center. But we got to run a quick check, which is actually test 3. I mean, it's not. It's just the way I teach it. I number 1, 2, 3. Okay. Does anybody remember the check that you got to check? It's also in it. You could also look at it and say, I know there's a chiral center, but I want to see, is this by chance a meso compound? A meso compound is one that has chiral centers, but somehow or another the molecule is still achiral. Does anybody remember how you test? It's got chiral centers, but I better double check. Plane asymmetry. Okay. You want to look for a plane asymmetry. Is there some place that I could chop this molecule in half, split it apart, and I'd have two equal pieces, two symmetrical pieces. Okay? Is there a plane of symmetry here? There's not a plane of symmetry. So we have a chiral center, we have no plane of symmetry. That is a chiral molecule. And what might have thrown you guys in the beginning is that I didn't do a wedge or a dash. That might have been like, oh, I'm used to thinking of chiral and stereochemistry with wedges and dashes. You don't have to. If you have a mixture of wedge and dash and wedge and dash, as we often do in chemistry, we often have a 50-50 mix of those. We don't tend to draw both of them because it's annoying. We tend to just say, ah, heck, let's just draw a straight line, and we will know that that means both of them. Okay? Make sense? All right. Okay, so let's talk about let's talk about sort of the run-of-the-mill type of reduction. Okay? Standard ketone aldehyde reduction. Okay. I'll show you the reagent, the mechanism, but for our talk today, one thing I really want you to take home is that if your reagent, if it's just a standard reagent, if it creates a chiral center, you're going to get both orientations. Okay? You're going to get wedge and dash. You're actually going to get a 50-50 mix of both of them. Okay? If you create a chiral center. Okay? All right. If reaction creates chiral center, okay, get both orientations. Okay? This is flat, right? That's trigonal planar. Okay? So the reagent can attack that carbonyl from inside the room here, or it can attack it can attack the molecule, the carbonyl, the flat carbonyl, from outside in the hall. It can come from either side of that. Okay? All right, so a couple different reagents that we can use to do this. Use a different color. Have you guys seen E.T. before? Not the fantastic movie from the 80s, but okay, yeah, it just means an ethyl piece. So it means CH2, CH3.
T?
E.T.
I thought that was a C. Yeah, me too.
Yeah?
Yeah.
Oh yeah, no, that's a T.
Okay.
Sorry. I don't know what EC would be.
It is either. I didn't want to question either.
E.T. E.T. Home home. Okay. All right. Couple different reagents we might use. The two most common ones that we teach are sodium borohydride and lithium borohydride. Boron and aluminum are funny atoms because if you give them a complete octet, you give them the 4 bonds that they need to get a complete octet, which makes everything happy, right? All the elements want a complete octet. If you give them a complete octet, but then you go and calculate and figure out what the formal charge is, remember formal charge? The formal charge is -1. So I always sort of describe boron, if you can't make boron and aluminum happy, okay? If If you take the bond off it, then it's electron deficient. It wants that complete octet, just like all the other atoms. Okay? But if you give it that last pair of electrons, it's got a negative formal charge, which also isn't very stable. So it's what we sometimes call that meta-stable. Stable-ish, stable kinda. Okay, which is nice, and we use that to our advantage to do reactions. Okay, so because you have that negative formal charge, these H's are not held on that tightly. Okay? And they can leave as a hydride, not a proton. This isn't an acid-base reaction. If something was going to come take a proton from this, it would just take the H and leave the 2 electrons behind. This is sort of the opposite. This is the H taking the electrons with it as a hydride. An H with 2 electrons, H minus essentially. Okay? You know that carbonyls, on the carbonyl carbon, it's got a partial positive charge. Sorry, that came out all blurry. That's a partial positive charge. So that lowercase Greek delta with a plus on it. Okay? So there's a positive charge there for 2 reasons. The oxygen's more electronegative than carbon. There's also a resonance structure that leaves a positive charge on that carbon. So overall, there's a strong partial positive charge there. That is attractive to this H minus. This H minus says, turn your polar on, you got a negative charge, you're all unhappy. I'm going to go attach to that carbon. That carbon's already got 4 bonds, so if something's going to attach to it, something's got to move. Okay? Now, essentially the hydride doesn't, it's not in the same plane. It actually kind of lands at an angle like this. Boom! Hits that carbonyl, pushes the H back, or pushes the oxygen back. Or comes from the hallway, boom! Pushes the oxygen towards you guys. Okay? So you get O that way, you get O that way. So that I don't have to draw 2 versions, I'm going to draw a squiggly. Okay? It's actually acceptable in the organic chemistry world just to draw a line, and that implies that you've got both. Okay? You actually have to go out of your way to specify, no, I got one, I got the wedge, or I got the dash. Okay? And so then, there's usually, I should have put it here, there's usually an acid step. Okay? And now this protonate. You get your final product. Does that make sense? Alright, the thing is that, like I said, this reagent has no preference. It will pick this side, or it will pick the hallway side. But if the reagent itself is chiral, it may have a preference. It may, nope, I wanna put the OET stuff, this stuff, I wanna put it right there, and then the carbonyl's here, and I'm gonna come from this side. Right? I want the OET on my right, and I'm going to come in from this side and push it back, or maybe the opposite. May want to come from this side, put the OET stuff, the ethoxy part, OET, on my left side, and then I'm going to come from the hallway. Okay? Just depends on the reagent. So if you can somehow create a chiral reagent, it will have a preference. That's the basis of what we're doing today. Okay? We don't want to make a 50-50 mix. We want to try to make one, either the wedge or the dash preferentially, the R or the S preferentially. Does that make sense? So all we need is a chiral reagent. Shucks. Okay. If reagent vital refers one side of the carbonyl out. And thus you get more of one orientation. This is actually a really important field in organic chemistry. A lot of the molecules that we try to make, we want to make them of a particular chirality. Okay? The things that medicines are going to attach to on our body usually are receptors. Receptors are most often made up of proteins that are made up of amino acids, and amino acids are chiral. Okay? You've probably heard of that lock and key mechanism for medicines and stuff. You know, the lock is the receptor and the key is the medicine. Okay? I think biochemists say that's a little oversimplified, but it's a good visual for us right now. So part of why it takes a special key to get into that lock is because that lock has a chiral environment, so it's got to have all the right wedges and dashes to get in. A really good take-home, a really horrible story, but a great take-home message of this is the story of thalidomide. Has anybody ever heard of that? Thalidomide was a medicine that they invented in the 60s for morning sickness, for pregnant women. It has one chiral center, and the correct chiral center worked wonderful for alleviating morning sickness. Okay? But you actually, for reasons I won't go into, you can't make, when you make this particular molecule, and not that many molecules are like this, but when you make this particular molecule, you cannot avoid making a little bit of the other stereochemistry. Okay? It was never approved in this country, but in Europe it was approved. And it turns out the one with the wrong chirality, just the impurity in there, caused horrible birth defects, caused the babies of these pregnant women to be born without limbs, without arms and stuff like that. So it's a great story, too, which I don't know because I'm a dummy. There was a very particular woman in the FDA who fought and fought and fought to not let it be approved in this country, and no doubt saved many Americans from having that type of birth defects. Okay, so in any case, it's an important field to make specific chiralities. You'll notice that a lot of the natural products that you guys are choosing for your literature talks will have a particular chirality, and when they do the total synthesis, they'll go out of their way, one way or another, to make the same chirality as the natural product. Okay, so how can we make a chiral reducing agent here? Well, I don't think it's probably surprising that hydride reagents are basic. An H- is pretty basic. Conjugate acid of H- is hydrogen gas, and that has a pKa of about 32, I think. Okay, so pretty high pKa means that was a pretty darn good base. So hydrides are pretty basic. Okay? So what you guys have done is you have taken tartaric acid, which is this guy, we can get from natural sources. Okay? Okay, that specific chirality, that's L-tartaric acid. That. And you combined it with sodium borohydride. Okay? To show how this works, I'm going to take this guy and I'm going to remember any single bond you can spin freely. I'm going to spin this guy around that bond and then that bond. Okay? So if I just rotate those around, what I come up with is this. Alright, well, these are carboxylic acids, okay? And you combine them with the borohydride, which we just decided is basic, which you can have happen. So one of these H's will, like you did before in my example, say, alright, boron, you're a mess. I'm going to go react with proton. Okay? And so it will grab that H. Okay. Now, as soon as the hydride grabs that H, little complainy boron is going to be like, I don't have a complete octet anymore. Okay? Then it is electron deficient, electron hungry. Okay? Well, this oxygen, he just lost his proton. Okay? The hydride came out, took the proton, it made hydrogen gas. That was the bubbling you saw, by the way. It was hydrogen gas. Okay. These electrons now, they are going to make a negative formal charge on that oxygen unless they find something else. Boron just lost his H and became electron deficient. So almost at the same time as that H goes out and grabs that proton, these electrons come and attach to that boron. Okay? So now you get boron still has 4 bonds, so it's got a negative charge. Okay. And now the same thing can happen with this proton and a hydride. Okay. So one of these hydrides will go, forget this, I'm out of here now. Just like my buddy grabs that proton. That proton gets grabbed, these electrons will pop down back onto that boron. Now you've created a cyclic structure. charge, it still has two hydrogens attached to it. So it can still, one of these H's can still break off, okay, and go attack something positive, like this carbonyl. So what you did in that first part of the experiment was you created this cyclic reagent. This is now a new reagent. You took sodium borohydride, one reagent, and L-tartaric acid, and you combined them to make this reagent. This is now a reducing agent. This is like a chiral sodium borohydride, right? Because it's got chirality back here. Does that make sense? And FYI, it probably doesn't sit flat like this, as we know from chapter 4 in your textbook. These things tend to make three-dimensional structures, and I put this into some software that tries to figure out, okay, well, what does this look like in 3D really? It's not going to be flat like drawn on a whiteboard. And what the software, so it's software a lot like what you guys did with the modeling experiment last semester. What it seemed to indicate is that this makes something similar to a chair. See sort of the chairness of it? Okay. So like I said, you've created a chiral borohydride reagent. That, when it's meeting up with ethyl acetoacetate, okay, it's going to have a preference. Does it want to put the O-ethoxy on my right side and come in this way? Or does it want to, put it on my left side and come in from that way? It now has a preference for which side, and so it will have a preference for, does it create a wedge or a dash here? Does that make sense, guys? Sort of, kind of?